Go ahead, get it. Okay, that's good. Yeah. Okay, so yesterday we derived the kind of discussed, not derived. This is called perturbation form of the equations because it's not linear. Okay, because this is nonlinear term, right? Nonlinear term, and this term can be ignored if we consider small amplitude. That means linear. Okay. So then we can ignore that, okay. And so if we ignore this, so let's probably do it term by term, okay. So 3.44, okay. So now if we assume, okay, u, okay. So if we assume, okay, if we assume u prime is much less than capital U. V prime much less than V. Okay, and that's linear. Okay, and then we also assume 2D. Okay, that means 3.44. The first term will remain same, and then second term will become U partial X, right? And then 2D, okay, our 2D is on X and Z plane. That means partial Y will be equal to 0. Okay, in Y direction there's no change. Okay, no variation. So we can ignore this whole term. Okay. And then the last one will become same, okay, the H prime, dx equals to 0, okay. And then second equation, 3.4.5 will become partial V prime, partial T, plus U, partial V prime, partial X, okay. And then third term will disappear because there's no variation in Y direction. The Y 方向没有 okay 没有变动 so okay partial V prime partial Y equals 0. Okay, so this whole term is gone, and this term is gone too. Okay, so become equal 0. Okay, and 3.4.6. Okay, you see. We also assume flat terrain, no bottom topography. Okay, okay, bottom is flat. So that means H sub S terms are gone. Right hand side becomes 0, and this term is 0. Okay, and this is gone. So we have the U prime, the T, plus U, partial U prime, partial X. Okay. And this term is gone because there's no Y variation. No Y variation, that means partial Y equals 0, right? Okay. And then let me know if you don't follow me. Okay, okay. Number one, okay. If you want me to use Mandarin or Taiwanese to explain, okay, you say this, okay. You say, Dr. Lin, number one, okay. And then this is gone. And then here, we keep H and H prime, okay, because H prime term will be nonlinear, so only keep H terms, okay, so H plus H prime, HS, okay, partial U, partial X plus partial V, partial Y, okay, this is gone, right, because 2D. Because 2D. Okay, so partial Y, no matter which equation, which variable is equals to 0. Okay, and it's 0. Okay.
3.4.6 is partial prime, partial prime.
Which one? First term? H prime. Oh, yeah. Thanks.
This thing is the same.
This one?
No, this thing of the.
Oh, yeah. Partial H. Yeah, okay. Yeah. That's good. That means people are listening. Okay. Not sleeping, right? Okay, and then, so then this will become H plus H prime times du prime dx, right? So this term, I'm talking about this term. I'm talking about this last term on the left-hand side, this term. So become like this. But this is gone because linear. Because it's nonlinear term. Okay. So then the last one becomes simple, very simple. This term become partial H prime, partial X, right? And then equals to 0. So the three equations reduce to this if it's two-dimensional. Okay, it's two-dimensional. Let me go down a little bit. Okay, if it's 2D, linear means small perturbation. So your perturbation could not be very large. Okay, that means U prime would be much less than basic wind. Okay, V prime also less than basic wind in y direction. Okay, 2D means partial y equals 0. Okay, so reduce to y moment, x momentum should be reduce this, and then this last equation become like this. Okay. Yeah.
Capital H
Partial. Oh, U prime. Okay, that's good. Okay, so this is U prime. Okay, like this. Okay, so we can erase this. So you may wonder, where does this go? Okay, where does this go? Okay, so this one actually is the V prime dt equals to 0, right? And ddt for two-dimensional will be just partial t plus u partial x, right? Okay, agree? Okay, so this is in simple way to look at is like in calculus. Okay, normally people write this way, ddt of v prime equals to 0. Okay, and so this means v prime will be equals to 0 to a certain time of v. Let me see. Integration. Okay, so we integrate dt of dt right. You can integrate this. We multiply dt here. Okay, and this is 0, right? This is 0, right? This is 0 times. Okay, so this is 0, right? This is 0 times dt. Okay, so this become like this. So this become t and dv prime, and this becomes v prime. Okay. Okay. So sorry, this becomes v prime at t minus v prime at 0. Right? Because the v prime equals to v prime. Okay. So if this is 0 to t, this means from 0 to t. That means v prime at time t minus v prime at time 0. Initial velocity. Okay, so this becomes this equation 3.4.5 becomes dvt equals to v prime 0. Okay, so initially, if you don't have y wind, then there's no y wind. If initially you have v wind, then that wind will keep same direction, so it doesn't affect our solution. Okay. But if you have rotation, that's different story. Okay, like so say here is ocean, and here's land. Okay, so your system could be like 2D, but okay, you can calculate v prime. Okay, for that problem, like so, like this, like when you in the morning, and then we develop the sea breeze coming in. Okay, and then if you have rotation, if this is just 2D, no rotation, it just keep coming in like this. So then everything will be identical in y direction. This is y direction. Okay, this is y direction. Okay, everything identical. Okay, but if you have rotation, then you start to have deflection to the right. Okay, so then the wind will be in the beginning going this way, eventually, okay, and then eventually become like this. Okay, you understand what I'm talking about? Okay. Let me try the Mandarin, okay?假设没有 rotation, okay, and then initially there's no V wind, then okay, so if initially have V wind, then that V wind at that time will keep same. Okay, 所以假设没有 Y wind， 那 okay, as time goes, V wind still same thing, so you don't have to worry about it. You understand? Okay, that's what this means. Okay, so basically you still have 3 equations. Okay, so now we just write down 2 equations because it's no concern to us. Okay, no change with time. Okay, once you have it, or normally you consider non-zero, then will be V prime also 0. But if initially you do have V wind, like in sea breeze, initially it's kind of blowing, 像 sea breeze 安怎讲？哈，海风 ，you sure？ 海风 ，OK 我伫阮兜帮了哦，一天到咧吹海风 ，OK， 海风 ，OK， 所以海风 ，OK， 海风这样吹过来，对不对？吹过来呢，如果有 rotation， 它就慢慢转成变成这样，到最后呢，变成比较 short balance。So then we'll keep doing this way. So you can still have V wind because here you have this U wind, and you have this V wind here. Okay, so you can have V wind, but V wind will be same everywhere, so it doesn't matter. So normally we ignore that equation. Okay, basically you still have with 3 equations, but we can just use these 2 equations, and then you can combine them into this one. Okay, into the 3.4.9. Okay, how many people have done this before? How many have this done before? Yeah. Okay, probably in which course? Oh, that's good. Okay, that's good. So you can, okay, combine them together, right? And how many have you derived this equation into that? Okay, from these two, 3.4.7 prime and the 3.48 prime to 3.4.9 prime. Have you? How many? No? Maybe we should put that into homework. Yeah. It's pretty easy, right? Okay, so I'm not going to go through it because that will take too much time. Maybe they let you do it, okay, at home. Okay, so now you combine into this equation. Okay, and this equation is okay, have a general solution like this. Okay, like this. If you don't believe, and f is any function. If you don't believe it, you should substitute this into there to see it works or not. Okay. Okay. So I guess I'm not going to do it. Okay, it's pretty simple and also take too much time. Okay, now assuming we have bottom topography. Okay. No, sorry, initial disturbance. So this f is any function. So assuming initially we have this perturbation. Okay. H naught and the p square divided by x square plus b square. Like this. So say if we have the shallow water like this, and this is capital H, so this depth, okay, and this is only one layer, okay, and so initially, if we have disturbance like this, okay, like this, and this is called the pear-shaped function, pear-shaped. Okay, pear-shaped function. Okay, so you have this, then the solution will be f of this. F now is this function, so then it will become, okay, h naught divided by 2 h square. Let me see. This is supposed to be b square. Okay, so b square. Supposed to be b square. Okay, so b square. Okay, and then become this x plus u minus square root gh. Okay, t divided. Okay, so you can derive that easily. Okay, as I said. Okay, any questions so far? Okay, that's good. Okay, so now and change this to be b square. Okay, to be b square here. Okay, yeah. So I'm not going to repeat that. I think that's kind of basic dynamics, and you don't understand. Probably can come to ask me. Or okay, I can show you, but for now we don't have enough time. Okay, so now if we consider we have a bottom topography. Okay, so basically what 3.4.14 okay says is this wave, okay, in the middle is going to break up into half of the amplitude and then propagate one rightward, one leftward. Okay, so this one will eventually break up into two, like this, and one propagate to the right, one propagate to the left. Okay, and this will be h naught. This will be h naught divided by 2. Okay, that's what this means. Okay, that's this means. Okay, divided by this. Okay, so I'm not going to spend too much time on that. My focus will be on the mountains. So right now, let's look at, if say we have kind of with okay, obstacle. So at bottom we have h sub s. Okay, then we are going to have additional term here. Additional term here. Okay. And now next thing is we are going to make one more assumption. We assume it's a steady state. Okay, steady state means no change with time. Okay, that means partial t will be equal to 0. Okay, no matter which variable. So now if partial t equals 0, then what happened? this will be 0, right? Okay, so let me write down there. Okay, so we consider 3.4.16. And now we assume steady state. Okay, steady state. 按照讲，哈？温态度，温态流，OK， 温态流 ，is that you don't know? You forgot, okay. Okay, so 3.316, okay, assuming steady state, 温态流 okay, steady state flow, okay, steady flow 温态流 okay, so 温态 okay, 温态 okay, so then that means partial t equals to 0, so then this will become u partial u square, partial square, and then h prime, right? The first term. Right? Everybody follows me? Yeah? Okay, and then second term, we still have gh, and then partial square, h prime, partial x square. Okay, and then this term, okay, it's mountain, right? Mountain normally doesn't fluctuate with time, so it's kind of steady state. But this kind of problem actually can apply to flow over 显峻, okay? 显峻 satchel, okay? Okay, because satchel bottom topography can change. Okay, so you can actually apply zero water equation to do satchel problem. Okay, but right now our mountain is fixed, so there's no for this term. Okay, so then it becomes u square, right? And then partial x, and then partial h sub x, partial x. Okay, so this actually becomes u square, partial h sub s, partial x square. Okay. So in other words, we have the square h square dx square minus gh the square h square dx square. Okay, and then the square dh dx square. Okay. And one rough way to simplify this equation is because we have partial x square, second derivative, so we just delete, okay, remove it. Okay, that's rough way, but rigorously speaking, you cannot do that. Okay, you cannot say, oh, every term has partial square, partial x square, then you just remove it. You cannot simply do that. Okay, you cannot say, oh, because we have this. So then we have u square, okay, h prime minus gh, and h prime equals to u square h sub s. Okay, you cannot do that. Okay, a lot of people do that. Okay, but theoretically you cannot do that. Okay, so what you do is you take integration. Okay. Assume or maybe assume far away negative infinity. Okay, negative infinity far away. So this is mountain. Okay, this is basic flow. Far away here. Far here is x equals to negative infinity. Okay, and then you negative infinity to x. Okay. And then gh is square h prime dx square equals to negative infinity to x, and u square d square h sub s dx square dx, yeah, dx here. Okay. Okay, so you have d square here. Okay. So then u square you can pull out, so it becomes u square, and then negative infinity, okay, like this. So then integral of, I'm talking about this term, square h prime dx square dx, that's equals to ddx, okay, of dh prime dx dx. Right, agree? And then this cancel out, okay, this become dh prime dx, negative infinity to x, negative infinity to x, negative infinity to x. Okay, so this becomes like this. Okay, and then let me see. This means dh prime x dx, and then minus at x. Okay, minus dh prime dx at x equals to negative infinity, x equals to just x here, and x equals to negative infinity. Okay, like that. So if you assume at phi infinity there's no terrain, then this term will be gone. Okay, so then this will reduce to the h prime dx. Okay, the first term. Okay, you do same thing here. Okay, that would be the h prime dx, and then equals to u squared dhs dx. Okay, and you do one more time. One more time. So the key point here is you have to assume, for doing this, you cannot simply say every term has the partial derivative of x, partial square and partial x square, and then you just delete them. You cannot do it. Theoretically you're supposed to do like this, and then you have to do assumption. One assumption is for infinity, there's no disturbance. H prime is 0. Okay, so you have to do that. So anyway, so okay, you do one more time, then. One more time, then this, okay, this will become u squared h prime minus gh and then h prime equals to u squared h sub s. Like this. Agree? Yeah, understand me? Okay. Okay, so now reduce this, and this one can be combined together because the left hand side we can combine to be u squared minus gh and then h prime equals to u squared of h sub s. Can you see me? Okay, yeah. Let me know if okay. Sometimes I forgot because when I was younger, probably younger than you, when I was younger than you, I went to a teacher's college, junior teacher's college, Sichuan. Okay, okay, and Sichuan, all I learned is gone. Okay, only thing I remember is, okay, when你教书的时候，你要 motivate 学生 ，OK， 要引起动机 ，OK， 好，这是为什么我一直讲笑话 ，OK。一直讲笑话，开北杜布 ，OK， second thing I remember is， 你在教书的时候哈，不可以看3板，不可以看天花板、地板，还有什么？白板，以前是黑板 ，OK， 所以不可以看3板 ，OK， so sometimes I do this, I have to be careful because people cannot see it, okay, so I have to stay aside. Okay, but sometimes I forgot. Anyway, so it becomes this. This is the final equation like this. Okay. Yeah. Right. Positive. Which one? Which one? This one? Yeah. If you are kind of considering easterly flow, yeah, you can do that. Okay, yeah. But normally you don't do that, right? Because x direction is to the right. Okay, but you can do that. But you have to.
But we can
You can change it, you just have to be careful because your U become negative. Okay. Your capital U is negative. Okay. I can erase, right? How many people are there? Huh? Still 4. Okay. We should get them an award. Okay, so they stick with us. They are probably students, I guess. Steady state, yeah, students, yeah. Steady state group. Okay, that's good, yeah. Okay, so become like this. Okay, and then H prime is U, is the perturbation height. Okay, to the water depth, capital H. Okay, so this means we have H prime equals to U square. U square is greater than GH. Okay, or U greater than square root GH. Right, then this will be positive. This will be positive. Okay, then if other situation is, sometimes it happens if U square less than GH or U less than square root GH. Okay, then this will become negative. Okay, so H prime will be proportional negative H sub S. Okay, yeah, I think we should take a break. Okay, and we'll continue after the break, 10 minutes break. Okay. Yeah. Okay, thank you for listening. We are going to take a 10-minute break. Okay, so Chào. Chào làm cái gì vậy? Oh, okay. Okay, so if U square is greater than GH, then basically what we have is, so these have two cases. Okay, then where H just simply equals to U square over U square minus GH times H sub S. Okay, if for the second case, then H prime will be equals to U square minus GH minus U square. Okay, and then in the beginning it will be negative, right? So this term inside bracket will be positive because GH is greater than U square. Okay, so like this. So there are two cases. Okay, yeah, and well, some of you probably are familiar with this. Okay, let me just do it something quick, like if we divide by U square on the right hand side. Okay, so then here this term, then this can be maybe this is a very simple thing. Okay, so this implies H prime equals to 1 over U square 1 minus square root GH over U square. Okay, so okay. Okay, so there are different ways you can do it. I just try to find a simple way for you to understand it. So this H prime equals to, if I divide by GH, okay, then it will be U square divided by GH, and then it will be U square divided by GH minus 1. Okay, H sub S. Okay, so now if we define okay, a number, okay, equals to u squared over gh. That means f will be equals to u divided by square root gh. Right. So then this will become what? This term will become f squared, right? Divided by f squared minus 1 h sub s. Or we can write as 1 divided by, okay, 1 minus 1 over f squared h sub s. Okay, and this is called the four number. Four number, how do you say in furusu? Okay, furusu. Four number. Okay, yeah, like this. So this means, okay, this means if u greater than gh, that means u over square root gh would be greater than 1. Right? Okay, right. And that means full number is greater than 1. This means full number is less than 1. Okay. So for short, if full number is greater than 1, then we have h prime equals to, okay, this h prime equals to u square over u square gh. Let me don't repeat. Okay, this is simple, just simply proportion to h sub s, because this is positive. Okay, f greater than 1. Okay, yeah, f greater than 1. F greater than 1. If full number, where these two cases less than 1, h prime less than proportion to negative h sub s. Okay, so those details I just kind of ignore it now. Okay, so this means what? This means you have disturbance, okay, for steady state, long-term disturbance, becomes steady state. Then if I have a mountain here, okay, and this is h sub s. Okay, that's mountain h sub s. Okay, like this. Then the perturbation here will be proportional to this. So when it goes up, it goes up. Okay, so it goes up like this. Not necessary to be same height, but will be proportional like that. So when you're mountain, okay, you go up. That makes sense, right? Okay, so if I have a mountain here, topography here, flow comes in, okay, flow comes in, let me see, depth, flow comes in, will go up, and then go down, okay. One thing strange is, so this is f greater than 1, okay. But when f is less than 1, the problem is this goes down. Okay, because this is h prime. Okay, this h prime is less than 0. Let's go down. Okay, because h prime is proportional to negative h sub s. So if we have mountain here, bottom topography here, this will become negative. Okay, so that is difficult to understand, right? Because flow comes in, and then when you have mountain, it's supposed to go up, but it goes down. Okay, so we're going to explain this quickly. Okay, so here, basically what we have is h prime equals to h sub s divided by 1 over 1 minus f to the negative 2. Okay, and f is defined as this. Okay, f is defined as u over square root gh. Okay. Okay, so this is a solution. This solution. Okay, now we wanted to find out what's the physical meaning of this. Okay. Okay, so f greater than 1, we have h proportional to mountain. So when you have mountain, okay, the perturbation will be just proportional to the mountain, not same height, but at least proportional. But when h is less than, f is less than 1, then it's going to dip down, passing over the mountain. Okay, so that's curious, right? That's kind of strange. Okay, so here I just make a kind of comment here is, maybe we can come back here, okay, because it is right now, I just try to make sure you understand the dynamics here. Okay, so this we're going to talk about that later on, okay. Okay, so here, look at these two, okay, cases. Okay, these two cases, okay, they're kind of steady state cases, okay. And so here, what happened is, your flow comes in with basic flow U, so then you have a kinetic energy is equals to 1/2 or times U, okay. And basically, actually, it's probably supposed to be 1/f rho times U squared. Okay, that's the kinetic energy. So you have kinetic energy here, and when F is greater than 1, that means U, F equals U greater than square root GH. That means U is large. The basic wind is very strong, and that means it's strong, have large kinetic energy. And that kinetic energy will be able to, okay, help the flow to going over. But when you're going over, because your elevation is, okay, your kind of height is kind of elevated, that means you have to convert some energy, kind of energy to potential energy. Okay, so just like, okay, if you're cramping, stand up here, you have to, okay, you have to kind of increase the potential energy. Okay, so part of the energy coming from the kinetic energy. Okay, so then, but this basic flow has enough energy to, okay, cramping over become part. You still have the kinetic energy, but part of the energy become potential energy, and then coming down, you convert back to kinetic energy. Okay, so that makes sense. Okay, so now how do you explain when you have dip down? It's because when it comes in, your U is not strong enough. Okay, so you don't have enough kinetic energy to cramp it over the mountain. So what's going to happen? Okay, so when I come here, okay, so I try to come here. Here's bottom topography. Okay, so say I'm flow, okay, particle come to here. I try to go over it, but I just don't have enough energy. Okay, okay, okay. So what do? I go down, right? I go down, and then I go down to go over, jump over. Okay, it's because you have to accumulate, convert your potential energy, okay, to convert part of it to become kinetic energy to go over. Okay, so then I try to go over. I have to go down and jump over. Okay, and that is okay. You kind of try to use part of your potential energy. You go down, right? Potential energy. Okay, 位能 ，OK， 降低位能 ，OK， 转换成动能 ，OK，go over. So then you dip down. That's why you got like this. And these two are the cases we see there. Okay, and here we have different cases, 3 or more cases, and they are kind of time dependent. So that their solution is not here. Why? When I solve this problem, very simple, right? Just algebra, no calculus. But when I solve it, this solution, do you feel like there's something there we don't really solve it? Okay. Is when this is equal to 0, you have no solution. Okay. We just assume it's non-zero. One is positive, one is negative. Okay. So when it's zero, what happened? Okay. When zero is called critical state. Critical state. It is zero, a critical state. So when you're critical state, you don't have steady state solution. So what's the solution cause? It's because it's time dependent. Okay. So flow is kind of transitional. Okay. Flow is kind of changing. Okay, with time. And so it's not in our steady state solution. Okay. So here that means no steady state solution. Okay, no steady solution. That's why you don't see it. You cannot solve it because it's zero. Okay, in the denominator. Okay, formula. Okay, formula is zero. You cannot solve it. And why? It's because it's not a steady state. And then you have three possibilities. One is this kinetic energy become potential energy, but then part of it become of kinetic energy. Okay, and then you have disturbance. There are two waves. One propagate downstream, one propagate upstream. Okay, so remember we talk about that we have this disturbance. Okay, and then part of it you have this one, you have this one. One is propagating downstream, one is propagating to upstream, and this one will go slower because you have basic flow coming in, so this goes slower. Okay, and this is called upstream propagating wave. And this one downstream propagating wave. And this one can develop into hydraulic jump, a jump, come down, because it goes down, downstream, okay, down slope, and then, okay, sorry, mountain is here, so this one will develop, okay, this one will develop into hydraulic jump, like this. This is called downstream propagation jump, this is called upstream propagation jump. And this jump is propagating. This jump is stationary. Okay, stationary. That means it's, how do you say stationary? Stationary. 静止. Okay. So yeah. So become 静止 hydraulic jump. Okay. And this one is when your U is become very very small to a certain point. Okay. Okay, cannot jump over. Okay, so it's totally blocked, cannot go over. Okay. So that go over. Okay, this one is just like when you go to the mountains or go look at the stream. Okay, a creek. Okay, shall see. Okay, and you see a lot of rock and flow. A lot of them cannot go over, so they go around it. Okay, because they don't have energy to climb it over. Okay, so this is called totally blocked flow. Total blocked flow, and this is called the kind of hydraulic jump. Okay, this one is stationary. This one is stationary. This is propagating. Okay, and both have the upstream propagating jump. Okay, and this upstream propagating jump could be very interesting. Okay, because you have a jump propagate against the flow. Okay. There are not many cases you have the flow, okay, you have the kind of flow can go against the basic flow. Okay, not many cases. Okay, and that is called sometimes it's called the bore. Okay, so I'm done here. Okay, the supercritical flow. Okay, this is called supercritical flow when flow number is greater than 1， flow 数大于1 OK， 那叫做 supercritical flow。supercritical flow how do you say supercritical flow？ 超临界flow。OK， 超临界流，超临界流。OK， 流 flow。OK flow。And that's called supercritical because this is critical, right? Equal 0 is critical. So if U square greater than GH, that means flow number is greater than 1, then that's called supercritical because this is critical state. Okay, so this is greater than 1. If U square is less than GH, that's below the critical. That's called subcritical. Okay, so we are done with those. Any questions so far? Oh, subcritical. Okay. Okay, so read this. When flow is subcritical, the flow number is less than 1. The steady state effect of this is to increase the layer depth upstream. Okay, because it doesn't. Okay, so say this is a mountain. This mountain, flow is coming in, but doesn't have enough kinetic energy to climb it over. So what's going to happen? Because then the flow is going to be blocked by the mountain, so it's going to accumulate. Okay, so when you accumulate, the water surface become higher. That means you increase the potential energy. To a certain point, you have enough potential energy to convert to the kinetic energy. So go over, but then dip down, go over. Okay. Because you have to convert into kinetic energy. You have to depart, part of your potential energy. Okay, flow comes in, being blocked by mountain, cannot go over. So gradually it kind of increase the height. Okay, so have enough potential energy. And then that potential energy, try to go over, then part of it have to convert to kinetic energy. That's why potential energy becomes smaller. Okay, dip down. Okay, so let me explain one more time. So say where U kind of small, that means flow number is less than 1. So flow is going to accumulate because it's blocked by the mountain, but cannot go over, so then will increase to a certain point. You've got enough potential energy. But this potential energy will be depart into potential energy plus potential kinetic energy. Over the mountain, it will become like this. MPS here. Over the mountain. Okay. So here, because this potential energy, part of it is going to become kinetic energy. So this part, PE over the mountain, will be decreased. Okay, will be smaller. Okay, so this PE will become smaller than PE upstream here. So because part of it go there. So if PE over the mountain, potential energy over the mountain is smaller than upstream, what's going to happen? It's smaller, that means its surface elevation will be decreased. That's why it goes down. That's why it goes down like this. Okay, so the fluid reach maximum speed. So here will be faster. Okay, like this. Okay, so here U will be less than U. Okay, so when U like this, it will be slower. Okay, and here U like this, here will be faster. Okay, so we are done with this. Okay, and you can also solve the steady state solution like this. U prime over capital U, is equal to -1 over F squared, H prime over H. you can also solve that. Okay, you can also solve that 3.4.19. That shouldn't be that difficult to derive. Okay, and this equation describes the Venturi effect, okay, also related to Bernoulli effect. Okay, what does that mean? Okay. Can somebody tell me what's Bernoulli equation, effect, Bernoulli? Bernoulli. Bernoulli, okay, Bernoulli, okay. Anybody knows Bernoulli, okay, effect? Low pressure, okay, yeah. And okay, lower speed flow will have higher pressure, okay, yeah. So, okay, so that's what they do, okay. Okay, do that, okay, right, okay, yeah. The pitch the baseball, okay. So they spin. So sometimes you feel like they go this way, but some kind of change go this way, okay. And some go this way, okay, because spin different, they will deflect, okay, because of pressure, okay, pressure, okay. So when you flow faster, that part will develop low pressure, and then you have pressure difference that give the ball has a pressure gradient force and then deflect it, okay. It's also sometimes they prefer to hire some left-handed touch wire, okay, yeah, because the spin is different, okay, difficult for the, okay, kind of hit, okay, to hit it, okay. So anyway, so that's related to Bernoulli effect, and here it's called Ventura effect, okay. They are related in a way, okay, yeah, because the Ventura effect is when you have h, okay, your h is your speed increase speed, you decrease the height, okay. You decrease the speed and then you increase the height, decrease the height, okay, there. So that basically is based on this equation. You have pressure, you have kinetic energy, you have potential energy, and all together is constant, okay. So if you keep height same, then pressure is proportional to speed, okay, negative speed, okay, and this is called Bernoulli effect, okay. If you keep same pressure, then the height and kinetic energy, okay, the potential energy and kinetic energy are inversely proportional, and that's what we're dealing with. That's called Venturi effect. Okay, they are related because they are governed by this equation. You're not familiar, please go home and then probably look at the book chapters or try to find it. Okay. And so in a transient flow, then we have different kind of cases happen. Okay. And then in that case, we also can define other non-dimensional parameter called non-dimensional mountain height. Okay, HM divided by capital H. Okay, capital H is undisturbed water depth. Okay, and HM is a maximum mountain height. Okay, and this is non-dimensional. Another one is flow number. Flow number is U over GH. So here we have two. So here we have two non-dimensional parameters. Where is two? Where is two? Okay, where two? Okay, one. Okay, one is M, and other one is flow number. Okay, and then they govern different flow regimes. Okay, so B, A here, the flow number is greater than 1. Okay, so that, and then E is less than 1. So these two are supercritical, subcritical flow. And P is this one. That's, we have hydrological jump, but that jump is propagating downstream. And C, we have hydrological jump, but it becomes stationary. Okay. And then D is okay, completely plug flow. Okay, because here, when you're D, that means your M is greater than 1. Okay, that means mountain is very high, and you don't have enough kinetic energy associated with the flow to go over it. Completely plug like this. Okay, so like you look at a creek, okay, a creek shall see, and you see a lot of rocks, and then flow keep down, go over, cannot go over, just go around it. Okay. Okay, so I think we are probably about done with this. Okay, so this is just real case. It happened in 1972, a very famous case, 1972, over the border. Okay, border is located to the north of Denver. Okay, about 1 hour, 45 minutes driving. Okay, so here. Here coming down, and here you go the subdental divide, the continental divide. Okay, okay. Continental divide is the highest peak over the Rocky Mountains, and then to the west, the water is flowing to the west. Okay, to the east, the water, okay, is flowing to the east. The river, okay, is flowing, okay, river water is flowing to the east, here to the west. That's why they call continental divide. And so border is here, and this mountain here. So they have flow comes in, they develop a strong downslope wind, okay, and this wind is very strong, called severe downslope windstorm, and that can reach 60 meters per second. 60 meters per second is typhoon wind, very strong. Okay. And also it go downstream or go down slope, it's very dry. So that can also create a problem because it's very dry. So if you have kind of fire, that can set big fires. Okay. And so this is like this. Okay, a kind of conceptual model is like you have upstream propagating jump, you have downstream propagating jump like this. Okay.
The upper part, the solid number, the solid line is similar temperature.
The potential temperature. Potential temperature. Yeah, potential temperature. Okay. And do you know those curves? You see those curves? Large curves. Do you know what that curves? What, because this guy's son or daughter kind of sketch it, play with it. No, it's not. They are flat. Okay, path. Those are flat paths. Okay, they observed. Okay, so it's severe downslope wind. This is, now you understand. Okay, so now this is a change of flow. Okay, and I'm looking to the south. Okay, this is Sierra Nevada. Okay, so flow come over from California, going and then develop a jump. Okay, and that's critical flow. Okay, for example, okay, you don't have solution for steady state. Okay, so you have downstream propagating jump. This one is probably stationary jump, coming down and jump up. Okay, this downstream jump. And sometimes you can observe the upstream propagating jump, that ball. Okay, you can observe that. One famous example is, have you heard of Chentangjiang? Yeah, Chentangjiang Jiangcao. Okay, that's okay, propagate against the flow. Okay, that's okay, it's ball. Okay, that's upstream propagating wave. Okay, jump. And originally I was trying to follow my mountain meteorology class in North Carolina. That normally we have 4 or 5 projects, but I think probably a little bit too overwhelming to you. And so what I'm going to do is I just will probably go with the first project and see what happens. Okay, we try to do this problem. Okay, so we try to do a project which will ask you to change the parameters. Okay, and you can change the mountain height. You can change the capital H. Okay, you can change U, capital U, and then to see if you can find those different regimes. Okay. So we are going to do a project to see if we can do that, can follow. Besides, also have the homework problems, but I kind of reduce the homework problems. Okay, yeah. I reduce it to just minimum number. Okay, so I let you read those. Okay, yeah. So later, don't worry about this. Later, we are going to study the severe thunderstorm wind storms when we talk about mountain waves. Okay, so we'll do that. But for now, I want you to have the feeling about those different flow regimes. So try to do a simple problem, and I'm going to give you as a gift the fortune program, so then you can look at that and then plot. Okay. And I probably need you and and you to help them. Okay, how to plot them. Okay. Running problem shouldn't be a big problem. You can go into that fortune program. You can change numbers. Okay. Nonlinear effects. Okay. If the nonlinear terms are kind of considerable, they cannot be ignored. Then, then then we want to understand what's the effect of the nonlinear effects. Those terms. Okay, remember when we solve the problem, we simplify the equations, but equations from the more complicated equations, which we have partial t plus u partial x. Okay, and then we have u prime. Remember that? Okay, and this, but this one is simplified from capital U plus u prime, and then partial u prime partial x, and this one we ignore it. Okay, that's called linearized equation or linear solution. Okay, equation. So we ignore it. If u much less than u, okay, if this is not true, then you have to include that term. And then you have nonlinear effects. Okay, so what's a nonlinear effect? Okay, so here I sketch in my book. Okay, I sketch in 2007. I sketch it like this. So say you have a wave like this, and then now you just imagine this wave is composed by 3 blocks, approximately by 3 blocks. Of course, you can use more blocks. You 100, just like a calculus, then become very close to the real amount. Okay, real wave. Okay, so just simply consider roughly we have 3 water blocks like this. Then, according to the shallow water theory, okay, according to shallow water theory, let me see, I think I need a book. Okay, Dr. Parent Lin, okay, I know you give that back to him, and he said he's going to bring back to me. Huh? Yeah. Oh, under his desk, and you can open his office. Oh yeah. Oh, can you get it? Yeah. Okay. That's what make it easier. So when let's okay. So let's do this. So this for this one, the depth of the floor is H1, right? Okay. So C3. Okay, we have the depth of the floor roughly like H3, and C2 would be like H2, and C1 would be H1. Okay, so here, so this is C1. So say here is H1. So C1 will be equals to what? Will be will be proportional to square root G H1. Right. Right. That's a shallow water with speed. Okay, equals to this. Okay. Will be, or say will be equals to this. This is called shallow water with speed. Okay. So, okay, this one. Okay. This one called shallow water with speed. Okay, shallow water with speed. So this shallow water with speed. And now, if on top of it, you have this, and then here you have H2, then C2 will be equals to what? Square root G H2. Right? So C2 will be greater than C1. Agree? Because it's deeper. Okay, deeper. So, okay, that deeper fluid will give you stronger flow. Okay, like this. So that means C2 will be bigger than C1, and C3 will be bigger than C2. So then, okay, so then what happened is C3 will be, oh, thank you. C3 will be larger than C2. C2 is larger than C1. So then C3 will be kind of flowing faster. So it's going to run in, okay, gradually catch up C2. And then C2 is going to catch C1, eventually going to like this. Okay, because C3 is moving faster. And C3, according to, just broadly speaking, according to the shallow water theory, C, the shallow water wave speed, is equals to square root of GH. Okay, that's called shallow water wave speed. And then, so then it's going to be overturned because it is far faster than this. Okay, so it's going to overturn it. Okay, and this is called steepening effect, and then eventually become overturning. Okay, and so now if you go to beach, okay, plain water, okay, and now you understand what's going on. Okay, that's beach wave. Okay, that's beach wave. No, it can be nonlinear. Yeah, it can be nonlinear. Yeah. Okay, we just use assuming linear, we assume steady state, and try to get simple solution to explain some basic dynamics. Okay, so when you go to the transient time-dependent flow, like the regimes on the right-hand side, they are time-dependent, they are nonlinear. Okay. Without linearity, you don't have the hydraulic jump. Okay. So say if you have So say this is so say this is beach, and here is water. Okay, and this is under the, okay, and this is a land here, okay. So here's water, right? So water, here's water. So water here, speed will be greater than here. Why? Deeper. Okay, see deeper. So your C will be equal to square root GH here. Here is C equals to square root GH here, right? So this H is smaller than this one. So this is also C2, H2, and C1, H1. Okay. Maybe I should write it more clearly so people over there, they can see it. Okay. So here, okay, your C2, C1 will be equals to square root GH1. And here will be faster. C2 equals square root GH2. Okay. So you're faster. So what's going to be accumulated because it catch up here. So that's why then you develop wave. You develop wave here. And wave will return over, and that gives you the pitch wave. Okay. This reminds me, I think there's one. Okay, I guess we are almost done. Okay, we are almost done in this. Okay, so now you may wonder why I wanted to spend time explaining this, because it's important for related to our real atmosphere flow. Okay, so you look at this. Okay, this is published by a graduate student at NC State, North Carolina State University with me. Okay, and he's in Taiwan now. Okay, yeah, I don't know if you know him. Okay, he's in the Kejibu. Okay, the Wang Tin An. Okay, yeah, Kejibu. Okay, so here, this is stratified flow, the atmosphere flow. Okay, so you can see flow. As time goes, you can develop hydrogen. If flow is faster, then you can go over this almost like supercritical flow. Okay, you can develop like this. Okay, and this is kind of hydrogen jump here. And here is, see here, black. And those lines are potential temperature. See here? Okay, because potential temperature, if there's no heating, okay, no cooling, no friction, then flow particle will be follow the potential temperature line, right? Because theta is conserved. So your flow will come like this, and then black. This is completely black. Okay, this is hydrogen, okay, stationary, and this is propagating. It's propagating because the basic flow is stronger. Okay, so you also have shallow water, mimic shallow water flow, not exactly. Okay, and when you have supercritical flow, difference is since we have great wave developed, and in the shallow water wave, okay, we don't have kind of this because we don't have stratification. We don't have density difference called stratification. Okay, 层 okay, okay, stratification. So then you develop great waves, and we are going to talk about great waves in next chapter. Okay. Okay, so this is probably a good time to. Oh no, not wait before you go. Okay. Oh, here just show you. Okay, because we have so many models, and we don't know they produce different results. So we do model comparison. So we did one model comparison. I participated in this one too. I'm a co-author of this paper, and every model kind of behave differently. Okay, so that's why we also need observations to verify the model to see which model is more accurate. Okay, and so that's why. And you can see, different model have different kind of behavior, but normally they all develop a hydraulic jump. Okay, hydraulic jump here. So now you don't understand this hydraulic jump here, severe downslope wind. You can have, okay, so we can have the downslope, severe downslope wind, and then hydraulic jump here. Okay, so almost everyone has that, participated. Okay, I use apps to participate. Okay, Dr. Huang used this model, Central University mesoscale model to participate. Dr. Huang Qingyong. Okay, and this is 2011. Okay, they also do similar thing, but over the kind of Sierra Nevada region, they have this. Okay, also different model. As you can see here, you don't have much going on, but here kind of very strong. Okay, so that's why we need a field experiment observation to verify. And then let me see. Let me close this. This one. Okay, so this is the homework. Okay, so you download homework, you start work on that. Okay, yeah, start work on that. Okay, so this homework number 1, you prove through point 3.1, 2.3.2, 2.3.3 are identical. Okay, I give a hint. And then second one is interesting because it's not difficult. The second one is you just based on 3.4.4, 3.4.6, you reduce, simplify the equations. Okay, and 3D you still assume 3D and linear, and one layer. Okay, one layer means you. Okay, you don't have 2 layers. Okay, so rho 1 will be equals to rho 0. Okay, so become simpler. Okay, so that means G prime will be equals to what? G prime will be equals to delta rho divided by rho naught times G. Okay, and rho naught delta rho will be equals to rho naught. Let me see. I know one. It becomes rho naught minus rho 1 divided by rho naught times G, but the rho 1 is equals to 0. Okay, so it becomes G. So you just simply change G prime to G. Okay, so equation becomes simpler, and then you follow what I did. Okay, so you follow I did, and then try to use the normal mode approach to derive the dispersion relationship, and then try to decide, also calculate phase speed, group velocity, and then try to decide, determine it is dispersive or not. If it's dispersive, if not, you also have to justify. You have to prove it. Okay, give that reason. Okay. And then number 3 is do this. Okay. And then number 4, no, number 4. And then project 1 will be doing this. Okay. I'll give you the equation. I'll give you the model, and then you change the parameters. and you plot it, and then to show, okay, the produce different regimes, okay, different flow regimes, okay. It's probably difficult to get this one, but at least you can get those 4, okay, or at least one of them, okay, and this one, and this one, and this, at least one of them. You can catch 2, would be the best. Okay. Yeah, so start to do the problem, okay. I think the homework you can start to do it now, and then for the project, okay, Chia-Hong is going to help you to, yeah. Okay.
How about the homework is due with July 4th?
July 4th. Probably 5th. Yeah. What do you think?
No, I just asking about the visa.
Huh?
No, I say it's due on July 4th for sure, right?
Yeah. Yeah. Okay. Yeah, because 1 day is equals to one week. Okay. So we're kind of very intense. Yeah. Because it's short course, so it condenses into 4 weeks. Okay, so 1 day is almost 1 week. Try it. We'll see what happens. Okay, yeah, try it. Yeah, you don't try, you never know what your potential is. Okay. Any questions, especially homework and any complaints? Too much? No? You haven't tried it, so you don't know too much. Okay. We'll see what happens. Okay. We'll see what happens. This one possibility is probably you can focus on 2 and 3, because 1 probably take a little bit effort. Okay, you need a more theoretical background, but 2 shouldn't be that difficult. Okay, 2 shouldn't be difficult. Okay, and 3 you should be able to do it. Okay, yeah. Okay, give it a try. Yeah, and then we'll do this project. But one good news is originally I was planning to have 4 projects. Okay. But then we probably just do this project. That's one good news. Okay. So you can start to do this. Okay, but it will have longer time. You don't have to submit by July 4th. Okay. So this one will take whole period. Okay. Any questions? This one? Oh, down. Oh, B is this one. And C is this one. Okay. Yeah. And E is this one. And A is this one. So what you can try to do, try to find those flow regimes. You have parameters. Okay. Your M and F. If you find M here, okay, F here, this F, right? So all these areas, the parameters, theoretically can produce, okay, this type of flow. In this area, this M. If M is here, then you have to find F in this area. If your M is here, you have to find F in this area, okay, this range here, and then you can produce region C. Okay, you know what I mean? What's your question? 你可以讲中文。
有到为什么它会水药会有水药
？Yeah, right. 水药现象，这样。
有到为什么？
会有 jump
会有这样子的。
哦现象哦 OK so question is why there's a jump there okay it's because when your flow comes in okay let me probably show you another figure let me show another figure okay chapter 3 right chapter 3 see here here these two are kind of critical okay so you increase the height of the water upstream so say this mountain okay so this mountain you increase okay and then that will increase the potential energy like this okay potential energy but this one okay since it's critical okay it's close to okay the square root GH is close to that U okay so it's critical so here you can develop a very strong downslope wind and when it's downslope wind rush downstream because downstream flow is slower so we have rush flow and then with strong convergence and develop jump you know what I mean so if you have a strong downslope wind rush down because ahead of it the flow is just capital U right basic flow and then that will try to push this one but this produce strong convergence and then strong upward motion that's why you jump today okay because you're very strong here okay because your potential energy okay convert to kinetic energy very strong and then flow here is slower so it's going to produce a lot of convergence and water has nowhere to go just go up okay jump up here that's called Hachio jump okay so I think we should stop okay and continue at 2 o'clock right 2 o'clock okay so the next topic is pure and inertial graded waves okay we will focus more on the pure graded waves okay and this one actually is similar to graded waves except you have the rotational effects okay included so as long as you understand the pure graded waves it's easier to understand this okay of course when I try to read the book I've been thinking to start with inertial graded waves and then assuming f equals 0 we reduce to pure graded waves but then later I changed my mind I think it's better to understand so let's start a new topic chapter 4 the pure and the inertial graded waves and as I just mentioned okay it's probably easier to go this way spend time understand pure graded waves and then okay automatically it will be easier to understand the inertial graded waves okay inertial graded waves you have the f non-zero okay the rotational effects come into play okay so maybe I should speak louder right that will help okay so first in this chapter we are going to derive the Taylor-Goldstein equation okay and so now if we look at the special case we look at this special case in order to understand it okay we assume it's okay small amplitude that's linear so it's linear and 2D okay 2D in a way in x and g domain. So okay, x and g, and so y direction will be 0. Okay, so this means partial y will be 0. Okay, so the you could have disturbance, you could have the variables, non-zero variables, but they don't change in y direction. Okay. So you still can have v equals 0, but v doesn't change in, okay, so in y direction. So we don't have to worry about that second equation. Okay. And so assume linear, implicit. That means no friction. And then non-rotating, okay. Non-rotating, so that's f equals 0. Okay, and then adiabatic. Okay, that means q, or sometimes I use q, small q equals 0. And Buzynsk. That means rho equals to constant except in the buoyancy term. And then we have uniform flow. Okay, so we have U of G equals to U. Okay, let me see. Oh, we are okay. We assume we have UG. Okay, so uniform flow like this. Okay, so then we have this set of equations. So we have these set of equations, okay, and then these set of equations will reduce, okay, to uniform basic flow. Okay, so uniform. Okay, U. That means U is equals to constant. Okay, it's constant. Let me see. Do I? Yeah, U is constant. Okay, so we assume no vertical winds here. So that means UG is equal to 0. No vertical shear. The horizontal wind, basic wind, okay, down shear. So then 2.24, 2.214, okay, we have the U prime. Maybe to save time, I can just use pointer. So here, okay, we have this term, okay, 2D, so this term is gone. So partial U prime, partial T, plus U, partial U prime, partial X. And then this term is gone, because no vertical wind shear of the horizontal wind, okay, that we call uniform wind, okay. And then F is 0, no rotation. And then here, this term becomes plus 1 over rho naught dP prime dx equals 0, okay. Because rho naught, rho bar normally is a function of height, rho of G, okay. But since we assume Buzynsk, so this rho bar becomes rho naught, a constant, okay. And then second equation, 2.2 or 15, okay, becomes partial V prime, partial T, okay, and plus U, partial V prime, partial X. And ddy, partial y equals to 0 because it's 2D, okay, so that's gone, okay. and this one is gone too because U and the G, there's no basic wind in y direction, okay, or okay, so or no vertical wind shear, so this is gone, okay. So we assume, okay, we also assume because 2D, right? Okay, so we assume, okay, V equals to 0, okay. So V is gone, so this term is gone, F is gone, okay. So then this one also 1 over. So we also have 1 over rho naught dp prime dy equals 0. Okay, but 2t, so this is gone. Okay, so this becomes equals to 0. Okay, so this same story. Okay, some story because if so, this becomes the v dt. Okay, equals 0 or dv prime dt equals 0. So that means v prime of t will be always equals to v prime of t equals 0. So once initially you have v prime, okay, it's going to be, you can have v prime, okay, but that will be constant, no variation in y direction. So basically this equation we can ignore. Okay. Yeah. However, if you have rotation, okay, if you have rotation, then we have v prime dt plus u dv prime dx, and then we have f u prime equals to 0. Okay, be careful. Okay, a lot of people don't know. Okay, even some senior scientists don't know. Okay, they normally assume two-dimensional. So with rotation, they still ignore that equation. You cannot. You have to include it. Okay, you have to include that. Okay, so this one you cannot ignore. You have to, okay, include it. But for 2D, for non-rotating, we can ignore this one because it's no change. Okay, so initially you can have v prime equals 0 or v prime not 0, but it doesn't change. Okay, so this equation we can ignore. And then 2.2.16. I don't like marker. Okay, I used to when I taught in Taiwan. Okay, I taught little kids in Taiwan. Okay, 6 years. Yeah, 教小学. Okay, and we use, okay, chalk. Okay, yeah, right, 粉笔. Okay, it's easier to write. And usually, no matter what I do, always ugly. Okay, my writing is terrible. Okay, so this one will become dw prime dt plus u dw prime dx. Okay, ddy is gone. Okay, and then we have this one mass g theta prime over theta naught. Okay, so we have to keep theta naught because that is corresponding to rho naught, rho prime, and rho prime doesn't exist here. There's no rho prime here, but we keep rho prime here. Okay, because theta prime over theta bar is proportional to negative rho prime over rho bar. Okay, in general. So we have to keep this. This is called buoyancy term. That gives us vertical oscillation. Okay, due to certification. Okay, and then this one, okay, become, let me see, and okay, this one become 1 over rho naught dp prime dg. Okay, and this one becomes 0. Okay, yeah, beyond 0. Okay, so let me see, so 2.216 become like this. Okay, it's theta naught. Yeah, it's theta naught, and then plus 1 over rho naught dp prime dg equals to 0. Okay, and then the last term you can prove this term is related to the sound wave, and you can prove it. This one is relative sound wave, and sound wave is very large, so this term become very small. Okay, so here, down here, it's relative to sound wave. Okay, wave speed. Yeah, and this one, okay, this sound wave, okay, it's very large, square. So this whole term is gone. Okay, and since it's Buzynsk, so rho is become constant. Okay, and then so this will become just this term. Okay, Buzynsk assuming your density is constant. Okay, except in this term, except this. Okay, this buoyancy term. Okay. So then, in that case, then you, okay, this will reduce to just, okay, a very simple equation. 2.2.17 will become, okay, du prime dx plus dw prime dg, because the dy is equal to 0. Okay, and q prime is 0 because it's adiabatic. Okay. And then last equation, 2.2.18. Sorry, my writing is terrible. Yeah, I don't like it myself. Okay, the theta prime. I don't know how to write because you do this way, it's not. You cannot do this. Okay, and then partial t plus. They probably should make this shorter. Okay, shorter so I can do this. Okay, plus u, the theta prime dx. And then dy is 0, okay, and then we have this term. Okay, that term becomes n squared and then theta naught because it's Buzynsk divided by g, okay, times w prime equals 0. Okay, yeah, so become simpler set of equations. Okay, so this is 3.5.1, and then this. Any questions? There any question? Yeah.
为什么2.2.2.2.1会变成连续方程式？
哦，变成这样是吧 ？Okay. This term is gone, right? Because C sub s is large. Okay, it's basically what Buzynsk means is like this. Okay, so basically your rho is equal to 0, is constant. Okay, except the buoyancy term. Okay, so this term is gone. Okay. And this is gone. Okay, so you can become like this. But let me see how to explain that. Okay, maybe better to look at the original continuity question. The original one was, I think everybody is down here. So the original one is 1 over rho, d rho dt plus, okay, del dot v equals 0, right? Okay, so then because rho is constant, rho naught, so this whole thing is gone. So look at this one, it's quite easier rather than look at, you always can prove it, but look at this one easier. So this will become partial u, partial x, plus partial v, partial y, plus partial w, partial g equal 0. Okay, but u is capital U plus u prime. So this term becomes partial u prime, partial x. And this one is gone because it's partial y. And this term becomes, and then w is equal to w prime. So then we have the w prime dg equals to 0, like this. Okay, so easier to just work on that. Okay, rather than go through that. Okay, so now we have a kind of set of equations with 4. Okay, 4 then, like 3.5.1 to 3.5.4. So these set of equations can be also combined into one governing equation of W prime. Okay, and it's just tradition. You can combine together as an equation of P prime or even U prime. Okay, but traditionally we use W prime. But in large scale, people more or less kind of combine into P prime. Okay. Okay, so those can be combined. Okay, I have explanation of this. Okay, this why the second equation can be ignored. It's there, but it doesn't change. V prime doesn't change, so you don't have to deal with it. But if it's rotating fluid, F is not equal to 0, you have to deal with it. You have to plus F term there. Okay, okay, for this one. So I explained earlier. So figure 3.7 illustrates the vertical oscillation of an air parcel in a stratified fluid with a Brown transversal frequency n. So this means this buoyancy term is important. Why is it important? Okay, because I think I explained this yesterday. Okay, in all the lectures. So when you initially here, you push it up by some reason. You push it up like air parcel being forced up. Okay, by the mountain, or it's been forced by a surface front. If a surface front and then passing through, air parcel will be pushed up. So once you push it up, it's going to go up, and when it go up, it's going to be expanding. Because of stratification. Because stratification, so we have lower fluid at the bottom, and and then density decrease with height. Density decrease with height, and then pressure will decrease exponential with height too, because pressure simply, the static pressure. Pressure is simply just like 1 square meter. And then the weight of the air column above it. So then when you go up, the air above it is less, so it's less pressure. So air parcel go up, the environmental pressure will be lower, so it's going to expand. Once you expand, then like a human being. So here, if the room is doubled, you got more freedom. So you don't bump into people more often. So air parcel go up, then the molecules will be bumping into each other less frequent. It's because the mean free path increases, right? Mean free path increases. So then you don't bump into each other. So you kind of fear. Oh, I'm so cold. I cannot talk to people. I have to yell at the people. In order to communicate. So it's getting colder. So once you get to a certain point colder, then it's going to sink down. So it's going to sink down. Sink down is not going to stop here. It's going to go down to here. So go down to here. And then it's going to be squeezed because your environment has higher pressure, so it can be squeezed. So just if somebody squeezes us into the corner, just like human being, right? So crowded. I don't feel comfortable. Human beings like this. When you have small space, you feel uncomfortable because you bump into other. But when you have huge space, you feel no companies. I'm so lonely, nobody to talk to. I have the ER to talk to my friends. So then we squeezed, and then become warmer because you bump each other. So the mean free path of molecules become shorter, and then so temperature increase. Temperature increase, it become hotter, lighter, and then go up. So this is the oscillation. This kind of vertical oscillation, this kind of vertical oscillation is going to influence the air above, air down. So then, it's going to energy is going to propagate away, above and down, below. Okay, so that's we call gravity wave because it's due to gravitational force, and that gravitational force gives us this buoyancy force. See, that's why we call gravity waves because this gravitational acceleration. Okay, that help to create, okay, density difference, temperature difference, and potential temperature difference. Okay, like it's like theta prime or theta bar or theta naught. Okay, is proportional to t prime over t bar. It's proportional to negative rho prime over rho r. Okay. Yeah. So this gravitational acceleration help to create this theta prime or t prime or rho prime. Okay. And then create this oscillation. And that's why it's called the gravitational. Okay. Gravity wave. Okay, so I think I already explained this. Okay. So then these four equations can be combined into an equation of W prime. And that equation is called the Taylor-Goldstein equation, okay, or Goldstein equation. Okay. And this is actually this is a simplified Taylor-Goldstein equation because, as you know, Taylor-Goldstein equation including the vertical wind shear. Okay, but here we have no vertical wind shear, so it becomes simpler, very simple like this. So is my voice okay? The sound, yeah. And how many people are there? 6 now. Oh, that's good. Yeah, we should celebrate. We get 2 more, right? Okay, so we have partial t plus u partial x square. N square x square. Okay, x square here, like that. So next topic is to try to identify, to study the flow regimes, okay, of the pure gravity waves. So to do that, we assume the wave is sinusoidal, okay, in x direction, it's sinusoidal like this, okay. And since it's sinusoidal, either sine function or cosine function, no matter which one, okay. Normally we just use a sine function. Some people use cosine function, it's fine, okay. Or in general, we can use exponent, okay. So then this one, okay, this one, for example, this one will have a wavelength of Rx, right? Rx, and then so you have k equals to 2 pi divided by Rx, okay, like that. And so then we can assume W prime is sinusoidal. So then we have W hat of g in x direction, okay, I kx minus omega t, okay. So as you know, this is equals to W hat, and then cosine of kx minus omega t plus I sine kx minus omega t, like this, okay, like this. So, okay, you can either cosine or sine, okay. In general, you have to combine these two and then substitute into it. At the end, you have to drop imaginary part to just keep the real part. Okay, but right now we just use this. Okay, substitute into it. Okay, so when you have ddt of w prime, okay, that would be, okay, so the w prime dt, that would be ddt of w hat of g e to the I of kx minus omega t. Okay, like this. Since this is independent of t, so we can pull that out. Okay, and then ddt of e to the I kx minus omega t. Okay, so that is equals to w hat of g. Okay, and then this whole thing, okay, e to the I kx minus omega t, and then ddt of I kx minus omega t. Okay, but this one is equals to I ddt of kx minus omega t. Okay, right. I just look at this particular one. And then kx is not a function of t, so it will be gone. And then so this become negative I omega. Right, I omega. So then we have negative I omega. Okay, that's this term, times w hat e to the I of kx minus omega t. Okay. So as you can see from here, when you take the w prime dt, we have this equals to this. But what's this? That's w prime itself. Okay. So this is equals to negative I omega w prime. Okay. And you do that for the w prime dx, that is will be equals to negative, will be equals to ik w prime. Okay. So in other words, when you have the ddt will be corresponding to, this is shortcut, okay, corresponding to negative I omega, assuming this kind of sinusoidal, and partial x will be corresponding to ik. Okay, this corresponding to ik times omega w prime. Okay, so you have ik. So then that's a shortcut. You can derive the dispersion relationship very quickly. Okay, everybody got this? Okay, maybe I erase this. Okay. So that means this equation will become, okay, ddt, partial t is what? I just erased it. Okay, it will be minus I omega. Partial x will be corresponding to ik. Okay, so plus u times ik and square. Okay, and then what's this? Would be partial w, partial x is corresponding to ik, but here is square. Okay, so we have ik square, okay, right, times w, okay, prime, okay, and then plus the square w prime dg square. Okay, and then this here become plus n square. Dtx is corresponding to ik square double prime equals to 0. Okay, in the wave number space, we call wave number space. Okay, here. Okay, and this approach is called, this method is called the normal mode approach. Okay, normal mode approach. Or method. Okay, assume this. Okay. Okay, so now we have that. So then we have I, negative I, negative I, and omega minus ku I omega ku, yeah, right. Minus I, okay. Okay, so then we have this square, and then times negative k square, 30 prime, plus d square, 30 prime, dg square. Okay, and here it becomes negative n square, k square, 30 prime equals 0. And this one becomes what? Negative I square. What is negative I square? It's 1. You sure? Minus 1, right? How many vote for minus 1? 2, 3, 4, 5, 6, 7, 8, 9. Okay. How about how many vote 1?
I k squared.
Yeah.
I k squared.
Yeah.
I k squared.
Yeah.
Total square.
Negative I square. Just 1 I. You sure? Minus 1, yeah. Okay, it's minus 1. Agree? Agree, right? Okay, good. Yeah. So this one becomes minus 1. Okay, so minus omega minus ku square. Okay. And then this one, we can just reverse. Right? So we have d square, 30 prime, dg square, minus k square, minus n square, k square, 30 prime equals 0. Okay. So we have 30 prime here. Okay. Okay, so now we're negative here, so it becomes plus. Okay. Okay, and then we can divide by omega minus ku square. Okay. So this one will come to here, the downstairs. Okay, the denominator. So then we have d square, 30 prime, dg square, minus k square, 30 prime. Okay. And then, okay. You know what should I do? What I should do is I probably would do this d square, w head, dg square. Okay, and then minus k square. Okay, and then w head, and then e to the I kx minus omega t. Okay, I do it this way. Okay, I can do it this way. Bye. Okay, and then here, and then plus n square, k square, divided by w hat here, e to the I kx minus omega t equals to 0. And here I just move this to here, omega minus ku square. Okay, so this is gone. Divided by e to the I times kx minus omega t. Okay, it's safe because you can remove it by divide non-zero value, okay, number. So then I think we are done here. We are done here. So then this one become the square w hat the g square, okay, minus k square w hat plus n square k square divided by omega minus k u square w hat equal 0. Okay, and so these two can be combined. Can be combined. Okay, can be combined. So then we have the square w hat dg square, okay, and then plus, okay, we can have k square here, and then k square minus ku, k minus omega minus ku square n square minus k square w hat equals to 0. Okay. Baik apa? Yeah. Okay, so if we define omega, capital omega equals to omega minus ku, okay, both are omegas. This is capital, this is, okay, the lowercase omega, okay, those both are Greek letters. And we define this omega as this, This omega is called Doppler frequency. Okay, you go with the basic flow and frequency. Or if non-basic flow, this is simply just omega. If there's a basic flow, okay, you just follow it. Okay, that's called Doppler. Okay, or sometimes we call the intrinsic frequency. Okay, so when you hear people say intrinsic frequency, that's Doppler frequency. That is, you don't count advection. You just go with the basic wind and then see the, okay, oscillation. So then this equation can be written as like this. And now this equation will be similar to shallow water equation. Okay. There are two different regimes. Okay. When the first term, n squared over omega squared is greater than k squared, you have one type of solution. And when n squared over omega squared is less than k squared, then you have different type of solution. So there are two different regimes. Okay, the wave behavior are different. Okay, the wave behavior are different. So if for okay case one, okay, if n square over omega square is greater than k square. Okay, then we have W hat, okay, of kg is equals to, okay, W0. I don't know the symbol there, but say we say W0, that would be equals to I times, okay, square root of n square divided by omega square minus k, okay, times g. This g is outside the square root. Everybody got this? Yeah. Yes? Yes? Okay, good. Okay, so then the second term will be W naught e to the minus I square root, same thing, okay, n square divided by omega square minus k, also k square here, k square times g, okay. And this is positive, so this is a real number, okay. Inside is positive, so here square root is real number. Second case, if n square, say this is second case, this is first case, okay. Doesn't matter, okay. Just to be consistent with my note, so you don't get confused. Okay, so n square omega square less than k square. This is first case, so that implies we have equation like this. Okay, so our equation can be written as d square W hat dg square minus k square minus n square, okay, over omega square equals 0. Okay, it's the same thing. Okay, it's same thing. I just reverse it because then this will give us positive value. Okay, this here will give positive value. I just write this way. Okay, so then based on the differential equation solution, this is different from this one. Okay, this one will have the solution like W hat of kg equals to W naught e to the square root k square minus n square divided by omega square times g. Okay, and then plus W naught e to the negative I square root k square minus n square over omega square times g. No I, like this. Here has I, here doesn't have I. Okay. So these are two regimes, okay. So we are going to talk about these two regimes, okay. Let me double check my solution is correct or not. Like this. So n omega greater than 1. Oh, strange. Oh, I missed there, okay. Nobody point out. I did it on purpose. Yeah, nobody point out. Okay, how come we have one there? Here. Okay, there's a k here. Right? So then we pull out. We're supposed to have one here. We're supposed to have k square here. Right? Okay, yeah. Okay, so here is supposed to be what? 1. Suppose one. One here and one here. Okay, the rest are same. Okay, and then we have one here. Minus one here. We have one here. We have one here. One here. We have one here. One here. Okay. Okay, so now let's take a look here. So n square, okay, over omega square greater than 1. Then we have this second case. Okay. Then we have this. Okay. AP, okay, is AP. Okay, to be consistent with AP here. So we have A, we have P here, and here will be different constant coefficient. Okay, and D. So these are the solution like this. Okay. So we have two cases. Okay, that give us two different wave behaviors like that. Okay. Okay. So then I think we should take a break, right? So we take a break for probably 10 minutes and then come back to continue. Okay. Okay. So actually, if you don't like, these two can be combined together. Okay. Okay. Because based on differential equation solution, you can simply just write as okay, A e to the img, B e to the negative img, and M is defined as m squared equals to k squared times n squared divided by omega squared minus 1. Okay, you can do this. Okay, you can do this. Okay, so okay, so this solution is correct, right? Yeah. How many vote for correct? You? Okay. You? Okay. How many vote not correct? Yeah. It's not correct. See here, when I rewrite in this way, I have a k squared here. So in the solution, we're supposed to have a k. Right? K here. K here. K here. Look at this. You see here? Look at this. You have a K here. Or you can write a K in the front. K here, K here, K here, K here. Okay. So basically you can just write, okay. Basically a simple way you can do is, I write this way is on purpose, make it more clear. Okay, there are two different flow regimes. Mathematicians, they probably don't care about that. Mathematicians, they will be simply just, okay, they probably simply just, okay, everybody got this, I believe. Okay, so mathematicians probably simply just write it this way. B square omega head BG square plus, okay, M square times omega square equals 0. Okay, and M square is defined as there. Okay, k square times a square minus, okay, divided by omega square minus 1. That's it. So based on this, mathematically, you can just use one solution. Okay, but I purposely on writing this way is make it very clear. Okay, in physical, in physics, okay, physical mechanisms, we have different regimes. So mathematician probably just simply write this way and then got the solution. W equals to like like A e to the I and G plus B e to the minus I and G. Okay, that's that. Okay, and of course, this one is identical to this one. But for this one, M is imaginary. Okay, imaginary. So then will be reduced to this one. Okay, so I do this way to make it easier to understand the physics. Okay, so now next thing is trying to see what's the physical meaning of these two solutions. So let's look at this one first. The case one first. Okay, so I have one of those. Oh, okay. Okay, so let's look at the. Okay, before I do that, let me discuss this a little bit. So now we have two terms. Okay, so in general, like this one, because it's second order in G. Okay, so that requires two boundary conditions. Two boundary conditions. What are they? One is at the surface. Okay, low boundary condition, top boundary condition. Okay, so the two boundary conditions will determine the coefficient. So as long as we have these two boundary conditions, that will give us A and B, these two coefficients. Okay, and then we have complete solution. Okay, so in order to have complete solution, we have to know the lower and upper boundary conditions. Okay. And also, this term, okay, we'll come back to there, okay, to that problem when we discuss the second case. Okay, so now let's look at, so you don't get confused. Okay, probably easier, I just do it here for you. Okay, so now, okay, so for we have the head of K, G equals to A e to the I, and then we write K in the front, square root of K square over omega square. Times G. Okay, plus B e to the plus I, K square root A square over omega square minus 1 plus G. Okay, so for this one, this is real number, right? So that means in height direction, in G direction, we have the sinusoidal disturbance. Okay, we have sinusoidal disturbance. Okay, because we have sine, cosine of G in vertical. Okay, for this one, Kg equals to C e to the mass e to the square root of I use pretty simple, then try to be consistent. I use K, okay. So I have K here, and then 1 minus n squared divided by omega squared times G plus T e to the minus K square root 1 minus n squared over omega squared times G. Okay. So in vertical direction, okay, it's not oscillating. Okay, so here the OF disturbance will increase with height. Okay. Here will decrease with height. So if disturbance is near the surface, then this term, okay, so say you have mountain here, this term is going to have amplify. Okay, this one, okay, this mountain, right, is going to decay exponentially like this term. Okay, so which one you want to choose depend on your boundary condition. Okay, your upper boundary condition will determine this term or this term. If disturbance is from lower level, like mountain, then this term is unphysical. Okay, and this one is physical. Okay, if it's disturbance from the mountain, because it decaying here, amplifying is impossible. Okay, we are talking about dry flow. Okay, over the mountain, right? So how can you, okay, a solution amplify vertically? Okay, so then we have this. So this is unphysical. Okay, flow over mountains. Okay, of course, if you have some there's some disturbance on top. For example, you have a bomb blow up, then it's different story because it's coming down. Okay, coming up is different. So here we have this. Okay, unphysical. We choose this one. So this one we call evanescent flow. Okay, and then that will give us. Okay, so this one. Okay, this will be unphysical. Then we still have one coefficient to determine. So what determines this D? The lower boundary condition. Okay. So upper and lower boundary condition are going to determine C and D. Okay, upper boundary condition if we choose. Okay, because if disturbance is from the bottom, okay, and then it's not going to amplify. Then we choose that boundary condition give us, okay, knock out this, and then become this. So this we call evanescent flow because evanescent, that means vertically it evanescent. It's not going to amplify. Okay. And so that becomes like this one. And then this D will be determined by low boundary condition. Okay, we'll talk about that in mountain waves. Okay, but this just give a general solution. And this one, okay, and this one, they represent different solutions. Just say, for example, flow over mountains. Okay, this one, this mountain. This one will give this solution. Okay, and this is called upstream phase tilt. The disturbance will tilt upstream because U is this way. Okay, and this one will have phase tilt like that, and repeating. Okay, we repeat. Okay, so later on we have Another one, so face tilt. Okay. And this one tilted downstream. And later we're going to talk about it. This one is associated with upward propagating wave. Your energy propagate upward. This one energy propagate downward. Okay. So which one is physical? This one. This one. Okay. Because our energy source is from surface near low boundary. So propagate upward. Okay. This one propagate down. That energy source is now from there. Okay. So choose this one. And this one we call this kind of solution we call vertically propagating waves. So you have two wave regimes. Okay. It's very important. Okay. Make sure you understand this. Okay, so this means the energy is going to propagate upward, and this boundary condition is called the radiation boundary condition. Okay, radiation doesn't mean the kind of the heat or cooling type of radiation. Here means the radiation of the wave energy. Okay, so that determines that we choose this term. Okay, choose this term. And this term for flow over mountains is unphysical because this one requires energy on top, but our energy source is the mountain. Okay. And this one, this boundary condition is called the boundedness conditions, bounded conditions, because this one will give us eventually become very minimal disturbance at top, but here amplify. Okay, so this is called limit. Okay, the boundedness. Boundary condition. Okay. The upper one. Okay, upper one. Okay, so these two regimes. One is evolution flow, one is vertical propagating wave. Okay, one question is, how come in this regime wave can propagate upward? How come here, kind of eventually become minimal disturbance? Okay. The wave amplitude decreases with height. How come? The key is this. The key is this. Okay. In this case, a square over omega square greater than 1. Okay. So that means n square is greater than omega square. Okay. And so this means n square greater than what's omega square? What's omega square? Omega minus Ku square. Okay, so probably I give you an example, easier to understand. For mountain waves, so assume after a long time, the mountain waves get established and become steady state. Okay, so how do you say steady state in equations? Very good. Okay, partial t. Okay, so steady state mountain waves. Steady state. That means partial t equals to 0. Okay. No matter which variable, of course, to w prime is 0. Okay. So what's partial t in the wave number space? What's partial T? Remember I taught you a shortcut. Okay. Okay, you go back to your note. Okay, what's partial T corresponding to? Right? Partial X corresponding to ik. So that means omega, okay, will be 0. So that means this term becomes 0. Because here we have I squared, remember that? Negative I squared, like that. Okay, so that I omega will be equal to 0. So this, for steady state, this becomes k squared, omega squared, u squared. Okay, so in other words, for steady state, our a squared greater than o squared is equals to a squared greater than k squared and u squared. Okay, so assuming here has two solutions, but assume just positive. Okay, for simplicity, so your n, k u, okay, like this. So like this. So what does this mean? This means we have 1 over n less than 1 over k u. Okay. And this means 2 pi over n less than 2 pi over ku. Okay. So here, let's say 1 over u. So what's 2 pi over n? N is Browne vessel frequency. Okay, so 2 pi divided by frequency, okay, that's the period. Okay, so this period is associated with buoyancy, vertical oscillation, buoyancy. And this one, what's 2 pi divided by k? That's wave length. Wave length. Okay, so this is equals to wave length. Okay, wave length. Like for example, you have a sinusoidal mountain. That's the wave length of the mountain. Okay, so you say you have a mountain like this, very simple one, sinusoidal one. Then this will be your L. Okay, and this is your U. Okay, so L divided by U is what? Period, right? The period, the time an air parcel is going to take to pass over the mountain. Okay. So this means Tp by T of advection. Okay, air parcel advection. So okay, like this. So this means advection. So say this is a mountain width. Okay, or the wave length, the mountain wave length. So L divided by U will be the time it takes the air parcel takes to pass over the mountain. That's advection. Okay, and that is greater than vertical oscillation. So air parcel passing this quick doesn't get changed to vertical oscillation. So your energy cannot propagate upward. So that's why you have this kind of wave. Okay, that's we call evanescent flow, because you don't get enough time to do vertical acceleration. You try to vertical acceleration, it's already passed the mountain. Okay. And on the other hand, for this case, will be just object, right? For this one, will give us TP will be greater than T elevation. So flow going slowly, passing over the mountain. So, okay, elevation will take a longer time to passing over. So when you air parcel try to pass over the sinusoidal mountain, it's going to have changed time to do vertical acceleration. So when you do vertical acceleration, you got energy propagating up or down. Of course, down is unphysical. We take upward. That gives us disturbance in vertical. Disturbances in vertical. Okay, and this one is the radiation boundary condition. Okay, because it allows us to have the energy propagating upward, also have enough time to do it because it takes longer time. It's either longer mountain or slower speed. So then you got the chance to do vertical acceleration. Okay, and then got energy propagate up or down. Okay, so that's two for regimes. Understand me? Okay, just like this. So for just example, for over mountain, later we are going to study this. But once you understand this general solution, then later on it will be easier to understand the real problem, the mountain wave problem. So this one is vertically propagating wave. Okay, so it's tilted, face tilted upstream here, flow coming from there. The face, we are talking about same face of the wave, like peak or valley, doesn't matter which one, or any point, but same face. And here, you can flow over, but then become evolution. It's tough, become weaker and weaker, because it's passing over the mountain quicker, so you don't get a chance to do vertical acceleration because of this condition. Okay, so that's okay. The two flow regimes. One is vertically propagating wave. It can propagate energy upward or downward, depend on your boundary condition. Okay, your radiation boundary condition. And or you have other regime which is evanescent flow. Okay, your energy cannot propagate away from the source or the disturbance because you pass quicker. You don't get a chance to do vertical acceleration. N is smaller. Okay, your kind of buoyancy force is smaller in this case. Okay, so next thing is try to talk about the phase and energy propagation.
I have a question about when you talk about the way propagate vertical. How come it's always
Downstream is this one.
yeah. I mean, upstream is
Oh, no, it's not propagate upstream. It's phase tilted upstream.
okay.
Yeah. Yeah.
Face
Yeah, the energy is going up. I think if you study the energy propagation, then you understand. That's why we have the energy propagation, because you have to calculate the energy propagation and particle motion. Particle motion gives us the phase velocity, and energy propagation give us group velocity. We have to look at those, and also we can have to look at the energy flux. Okay, energy flux should be upward. Okay, if the source is in lower level. Okay, if source is in upper level, then energy propagation would downstream downward. Okay, and that group velocity will be downward. So now next thing is let's take a look at this one. This governing equation in the wave number space. Okay, so we have the square W hat dg square plus a square over omega square minus 1 and times k square, and then W hat equals 0. Okay, so if we assume W hat is equals to W0, okay, e to the I and G. So, okay, in other words, if in the beginning we have W, okay, equals to W naught. Remember we have this, we assume W hat of G e to the I kx minus omega t. Remember that we assume this. If in the beginning we assume W equals to W naught e to the I of kx plus mg minus omega t, then we can just use this, plug into the original, okay, the Taylor's ghost time equation. Then it's the same as here. We just use two steps. Okay, because these two together will be given this. Okay, these two together will give us this. Obvious is m. Okay, we just do two steps. Okay, you can do one step. Just put this into there. Okay, get the same solution. So here, so we have ddt corresponding to negative I omega. dtx corresponding to ik, dtg corresponding to what? Im. Okay, Im because of it. So you substitute into there, you got Im square W hat plus n square minus 1 k square, and then W hat equals 0. This gives us, okay, Im, okay, that's negative m square, and then plus k square times n square divided by omega square minus 1 equals to 0. Okay. So this one can be, okay, reorganized. Okay, so now we have this n square over omega square minus 1. Okay, and then plus minus m square divided by k square. Okay, equals to 0. Okay, so it's equals to this. So this gives us n square over omega square equals to m square k square plus 1. So that gives us m square plus k square divided by k square. Okay, so we just, okay, turn around. we have omega square divided by n square equals to k square divided by m square, or k square plus n square. Okay, so this gives us omega square equals to, okay, k square times n square divided by k square plus m square. Okay, so omega equals to, we take square root, we have two solutions, kn divided by square root k square plus m square. Okay, so omega is wave frequency, the intrinsic wave frequency, or Doppler wave frequency. Okay, equals to this. And then this is called dispersion duration. Okay, dispersion duration. Okay, or sometimes people call it dispersion relationship. Okay, I ask Americans, they don't know the answer. Okay, but okay, what's the difference of relationship? Sometimes people use dispersion duration. Some people use dispersion relationship. It's okay. Okay, people use that. Okay. But normally, relationship, you're talking more, okay, with person, okay, and relation can be any general business. Okay, so normally, okay, but sometimes you also see I use relationship. Okay, but that's what my American friends told me. Okay, so the dispersion duration, okay, for pure quadratic waves like this. Okay, next thing is, so for a quiescent fluid, that means there's no basic flow, okay, then capital U equals 0, then this become omega, right? Become omega. So small omega. So become small omega. So now this is small omega divided by n will be equal to positive omega k divided by square root k square plus m square. And okay. And then what's the right hand side of that equation? So if this is x, okay, and this is g, okay, then that means, this means, okay, if we have the wave number vector that is equals to k m. This is horizontal, this is vertical. Okay, this is a vector, and that means it's like this. So this is k, okay, like this, and this will be k to m. Okay, so here would be square root k square plus m square. So k divided by square root k square plus m square is what? It's cosine alpha. If this angle is between horizontal x direction and wave number, okay, vector is wave number vector, then that's why we have this cosine alpha. And then we have positive negative, so positive negative cosine alpha. So alpha is the angle between the wave number vector and the horizontal direction. So what is that alpha actually? It's like if we have a water tank here, and if I put a stick and then with something at the end, and I kind of disturb it, that's called wave generator. We generate wave, right? Okay, we generate wave. If it's water, okay, your wave probably just go up and down, but it is stratified fluid, okay, then you generate it, then so you have a water tank like this water, your oil generator, like that. It's certified. Okay, certified fluid. Then you're going to generate waves, disturbance. Okay, and this is alpha, and that determined by n omega n and omega, because now quiescent, there's no basic flow, so determined by what? By k omega by n. How strong is your stratification? Okay, and also your omega. What's omega in this case? It's how fast you generate. You can do slowly, you can do faster. Okay, and that will determine, okay, how large is this angle alpha. Okay, generate out. Okay, so say let me draw that. So this is water, right? Water. Okay. So now if I have generator here, it's going to generate waves. Go this way, go this way, go this way, go this way. Okay, so I have wave like this, wave like this, wave like this. Okay, wave like this. Okay. So if this oil generator is not a stick, it is a mountain here. So this is the air. So say this is air, this fluid become air. And then below will be below mountain, so those are just earth. Then you only have, okay, this wave and this wave. Okay. And this, okay, these two waves, and they represent, okay, okay, upward, downward propagating. Okay, and for mountains, okay, you do upward, downward propagating. So you have face kind of tilted upward or downstream or upstream. Okay, like that. Okay, in a simple way to say, we're going to make more explanation of that. Okay, in the next chapter, probably next chapter. Okay, so here probably we can just talk quickly to understand this. So here is you have this extension, okay, and this alpha, okay, this case wave damper space, that means your wave will propagating to here, to this direction. And then you can calculate the CG, okay, because CG will be simply, okay, CG will be simply equals to the omega, okay, and then the K, this is in X direction, in G direction will be the omega, the M, okay, and that can determine your, okay, kind of CG direction, okay, and CG you can calculate it based on the dispersion direction. You can calculate CG and CP, and you'll find CG and CP are just vertical, okay, perpendicular. So your CG go like this, and then, okay, wave go this way, energy go this way, but wave you see is go this way. A little bit difficult to understand, okay. The kind of great waves a little bit hard to understand because they have very complicated situation. It's like unlike like sound wave. Sound wave, you compress it, you expand it, and then they just go, okay, same direction, okay, go out, okay. But here you oscillate, okay, you oscillate this direction, and the wave can propagate vertically, okay, perpendicular to it. So you have this. And also based on the equations, we can derive the relationship between W prime and theta prime, and that can determine where you're going to have cold region, warm region, and you can have P prime relation with W prime. That gives you where is high pressure, where is low pressure. That's why we have those high, low, cold, warm regions. And how to do it? Okay, you can go down here. Okay, so you can find the phase speed in x direction, in g direction. See here, in g direction. Okay, you can calculate, right? Omega divided by k, omega divided by m. That's pretty easy. Algebra, no calculus. And for velocities, you can take partial omega partial k, partial omega partial m, like this. Okay. So now, this is very important. Okay. This has very important applications to NWP, numerical ways of prediction. Okay. So you take a look at in x direction, CP, x, and gx. They are not identical. They are not, but okay. But they are in same direction. See here, when you're positive n, you're positive m squared times n, and downstairs same. Here, oh, not same, but okay, this is positive anyway, so they're same direction. If negative, it's negative here. Okay, and in g direction, when you're positive kn, okay, we have negative kn times n, kn times n. And when you have negative here, sorry, okay, yeah, you have negative here, phase speed downward. Here you have positive. Okay, what does that mean? That means in a numerical domain, okay, a matter domain. Here, when you have CG go upward, your CP is downward. Here, CGX is same direction as CPX. Okay, so what does that mean? That means they are same direction. So horizontally, we can use the advection equation to advect energy out because they are propagating in same direction. Here you cannot. So you have to apply the sponge layer or upper radiation boundary conditions to take energy out from the disturbance generated within that domain, matter domain. Okay, so that makes big difference because here you can just simply use partial y, partial t, plus c, partial y, partial x equals 0. We just solve this at the boundary. You can simply advect the energy out. You cannot do it here. Yet it's more complicated way to do at the top. Okay, so that's a strong application to the numerical model NWP. Okay, so I have explanation here. Okay, please take a look. If you have questions, let me know. Okay. Okay, and this upper boundary condition is called Sommerfeld. Okay, radiation boundary condition. Okay, because it was proposed by him. Okay, so then based on this solution W, okay, you have to take real part because imaginary part is unphysical. So you have to take a real part and then become like this. And then based on this, you can calculate theta prime, and you can take you can calculate everything: U prime, P prime, theta prime, and then those are called the polarization relations. Okay, so don't be nervous if you. This is more theoretical, okay, and more related to fluid dynamics. So don't panic Don't worry. Okay, because later on, when we talk about the steady state mountain waves, okay, we can see this very clearly. Okay, it's easier to understand. Okay, so now if you can understand, that's best. Okay, doesn't mean you have to speak Taiwanese. Okay, but okay, you can understand that best. If not, don't worry too much because in mountain waves, okay, we are going to talk about simpler solutions, which is steady state, okay, flow, and that we also can derive U prime, P prime, theta prime, and it will help you to understand this better. Okay. So in other words, when you understand that later on we are going to talk about, then come back to here, you will be okay, understand this better. So don't worry too much if you don't understand, but you understand that's the best right now. Okay, so probably I'll stop here because already 4 o'clock. So we are kind of start here. Next time we're going to talk about these two flow regimes, two extreme cases. Okay, what are they in the flow behavior? Okay, so we'll stop here. Okay, well, thanks for listening. Okay, thank you. How many people?
10 people now.
Huh? 10 now? Oh, thank you very much. Okay, yeah. So talk to you, see you tomorrow.